Today I'll be talking about the paper on generative spoken language modeling from audio. Children learn to speak before they can read and write. The question is, can we build AI systems that learn from natural interactions as infants, learn from their first language, from raw and uncurated data without access to text or expert labels? The natural language processing systems are currently far from this requirement. And there's progress in reducing and eliminating the need for expert labels through self-supervised training objectives. However, basic training unit is still textual. In this paper, the authors claim that treating text NLP would benefit in language that do not have large textual resources or even widely used standardized orthographies such as Arabic. Building an entire dialogue system from audio only is a difficult challenge. Unsupervised representation learning may address part of it. The idea is to use learn discrete units instead of label phonemic or textual units. Unsupervised representation learning learns continuous or discrete units that capture speaker invariant phonetic contents, which are not phonemic. The paper presents a generative spoken language models that consist of three components. A speech encoder, S2U, discovers discrete units or pseudotext from speech. A unique language model, ULM, is trained on the pseudotext units to discover language patterns. And lastly, a speech decoder synthesizes speech from discrete units. These systems allow building a language model from scratch without text and use this to generate speech. The main approach is to use autoencoder to learn discrete units. The issue is how we can evaluate the quality of the learned unit or pseudotext. Text-based models have common metrics such as perplexity, but pseudotext-based models don't have any. Conceptually, the generative spoken language models can be evaluated at two levels: acoustic level or intelligibility, and language level, meaningfulness. The idea is to use a pre-trained ASR to convert synthesized speech into text. As a result, common metrics can be applied. In this section, we present the architecture of a generative spoken language model and how to evaluate such model. A generative spoken language model has three components. Firstly, an acoustic unit discovery encodes speech into discrete units, discarding non-linguistic factors like speaker and noise. Secondly, a unique language model represents the probability of language patterns in a spoken language modeling task. And finally, a decoder resynthesized input speech in a discrete resynthesis task or synthesized new speech from sampler units. In a speech generation task, the authors evaluate intelligibility of speech resynthesis tasks. To do so, they apply a pre-trained ASR and resynthesize speech to compute phone error rate, a PER. The author also evaluates the meaningfulness of speech generation tasks. They also use a pre-trained ASR to convert resynthesized speech into text. Then they evaluate the quality of text using mean perplexity or negative log likelihood and the diversity of generated text using cell blue matrix. A metric aims to assess how similar two generated sentences are. But there's a trade-off between quality and diversity of generated text. A temperature hyperparameter is used to control the trade-off. Low temperature outputs good sentences, but not varied, while high temperature outputs varied sentences, but not good. The authors observed that at low temperature, cell blue score stopped increasing, but repeats more and more words within a sentence. For example, the property, the property, the property. The authors introduced auto blue metric that measure within sentence diversity. Auto blue is calculated as ratio of k-grams that are repeated at least once. For simplicity, the authors use bigram, self, and auto blue. The author defines verb as the mean of self and auto blue metrics. The figures shows the trade-off between quality and diversity of generated speech under different value of temperature parameter. The x-axis is mean perplexity or accuracy, while the y-axis is the diversity. An orange line shows the trade-off between accuracy and diversity. And we can see that increased accuracy means decreased diversity, and or otherwise. The blue diamond corresponds to oracle point, a real text. And we can see the green area and the third AUC in this figure. Lower AUC is better. For cross-model comparison, we select the temperature at two boundaries for two boundaries. The first at oracle perplexity and perplexity at oracle vert. So different model will have different temperatures to best trade-off between quality and diversity. For evaluating the quality of pseudo-text units, the author used two zero-sort metrics. For acoustic level, ABX score is used to quantify how well separate phonetic categories are. For language model, spot the word accuracy is used to detect real word from a pair of source utterances like brick and blick. Human evaluation is the best way to assess speech intelligibility and meaningfulness. Into MOS tests, participants listen to stimuli and answer how intelligible or meaningful they are. In a 5-point scale, for speech to unit components, the authors use the baseline of 80-band log-mail. They also use powerful pre-trained speech to unit encoders such as contrastive predictive coding, Weidelberg and Hilbert. Contrastive predictive coding encodes 10 millisecond speech into 256-dimensional vector. Weidelberg encodes 20 millisecond speech into 1024-dimensional vector. Hilbert encodes 20 millisecond speech into 768-dimensional vector. K-mean is used to convert these continuous vectors into discrete unit, and K can be 50, 100, or 200. For unit language modeling, a generic transformer is used. Finally, for unit-to-speech modeling, the authors adapt pre-trained Dakotron 2 and Wakelow with different discrete units come from different encoder. In this section, we present the experiment results in this paper. Looking at the bottom, middle, and right figures for resynthesis task, increasing numbers of units lead to better phone error rate and MOS. Hilbert and CPCs seem to give best results. Objective metric like PER and human opinion MOS correlate well. For generation task, 50 units is the worst, but 200 units is not always better. Human evaluation shows similar pattern with this preference for 50 units, either 100 or 200 units being better. The table separates results on LS and LJ evaluation tests in resynthesis task. The S2U encoder is trained on LS training sets, while the U2S decoder is trained on LJ training set. So we expect in-domain effect on LS and LJ evaluation set. Top lines show the upper bounds for resynthesis tasks. Original text plus text-to-speech shows the quality of synthesized speech from text. ASR plus TTS shows the quality of synthesized speech from ASR outputs. As we can see, baseline log mail is the worst. We can also see that resynthesized speech from LJ yields lower PER. Although LJ speech is out domain for the encoder, the decoder compensates for the low quality units. We can see that The best system, such as Hubert or CPC, come very close to the top lines in terms of phone error rate and character error rate. Also very close in terms of human opinion. For generation tasks, as expected, the perplexity metrics are improved when sampling language model with prompt. For example, the perplexity of CPC 50 reduces from 374 to 323, and human evaluation also agrees with the objective metrics. For unit quality, zero-shot metrics shows that Hubert is the best. Interestingly, zero-shot metrics like ABX strongly correlates to ASR-based and human metrics. For example, the second row, ABX across correlate well to phone error rate, character error rate, and MOS. Therefore, we can use ABX metric as a proxy metric for preliminary model and unit size selection because it's less costly than ASR-based and human metric. In conclusion, the paper introduced generative spoken language modeling. The authors established ASR-based metric for model comparison at two levels, intelligibility and meaningful needs. ASR-based metrics correlate well with human evaluation. Objective metrics confirm the quality of learned representations. Using 200 units is optimal in most cases. The authors also proposed a method to select temperature, which controls the trade-off between quality and diversity by using Oracle text. Thanks for your attention.